Reversible reactions are those reactions which proceed in both forward and backward direction. They are represented by a double-headed arrow. If, in a reversible reaction, one or more components are gaseous, then the reaction must be performed in a closed system or a closed container. All reversible reactions will acquire a state of dynamic equilibrium at which the rate of the forward and the backward reaction becomes equal and there is no net change of concentration of any component on any side. Every reversible reaction will acquire the state of dynamic equilibrium at its own specific set of conditions. There are three main factors that affect dynamic equilibrium: temperature, pressure, and concentration. But you will often find questions that involve changing the volume. However, that is simply linked to pressure. The Le Chatelier's principle states that if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counteract the change. Which means that if an internal constraint is applied on a system at dynamic equilibrium, the system will oppose the change to neutralize the constraint. If the concentration of any component is increased at any side of a reversible reaction, the equilibrium will shatter and the reaction will shift its direction to the opposite side. If the concentration of any component is decreased at any side of a reversible reaction, the equilibrium will shatter and the reaction will shift its direction towards that side. Over here, if I increase the concentration of dinitrogen tetroxide, then the equilibrium will shift towards the product side and more nitrogen dioxide will be produced. So it means that the forward reaction will be favored when I increase the concentration of dinitrogen tetroxide. Moving on to pressure. Pressure can only be applied in gaseous state. By increasing pressure, dynamic equilibrium gets disturbed. It will shift in the direction where there are less moles of gases or less volume of gases, and the decrease in pressure favors the side where there is more volume or more moles of gas. In this equation, what happens when we increase the pressure? So first, let's calculate the moles of gases. You can calculate the moles by just looking at the number before each molecule. Before N2, you have no number, which means that there is 1 mole of nitrogen. Before hydrogen, you have 3, so it means that there are 3 moles of hydrogen. 1 mole of nitrogen and 3 moles of hydrogen react to form 2 moles of ammonia. So on the reactant side, you have 4 moles of gases, and on the product side, you only have 2 moles of gases. We studied that when you increase the pressure, the equilibrium shifts towards the side with lesser moles of gas. So over here, the product side has fewer moles of gas, so equilibrium shifts towards the product side, which means that the forward reaction is favored and more of ammonia is produced. If the volume or the moles of gases are the same on both sides, then there will be no effect of pressure. For example, in this equation, both sides have 2 moles of gases, so pressure won't affect the equilibrium. Moving on to temperature. An increase in temperature favors the endothermic side or the endothermic reaction, and a decrease in temperature favors the exothermic side or the exothermic reaction. How can I tell which side or which reaction is endothermic? If the enthalpy change of that equation given is positive, then the reaction is endothermic. So increasing the temperature will favor the endothermic side. So the forward reaction will be favored. A positive enthalpy change tells you that the forward reaction is endothermic and the backward reaction is exothermic. So if in such a reaction you increase the temperature, the forward reaction will be favored, but if you decrease the temperature, the backward or the exothermic reaction will be favored. Over here, the enthalpy change is negative, which means that the forward reaction is exothermic. If I increase the temperature, the backward reaction will be favored, which means that more nitrogen and hydrogen would be produced separately. And if we decrease the temperature, then the forward reaction or the exothermic reaction will be favored and more ammonia will be produced. The reaction we are looking at right now is for the Haber process. The Haber process is an industrial process of manufacturing ammonia from nitrogen and hydrogen. 3 moles of hydrogen and 1 mole of nitrogen make 2 moles of ammonia. Since this is a reversible reaction, some ammonia is decomposed back, and we try to keep that amount as minimum as possible by changing the condition. Over here, hydrogen is obtained from cracking petroleum hydrocarbon chains. In a reactor, hydrogen and nitrogen are reacted. To obtain ammonia, the gas mix is cooled to negative 34 degrees Celsius when ammonia liquefies. The hydrogen and nitrogen, the unreacted gases, are recycled. Now, if we want a maximum yield of ammonia, we need to change the conditions. We can increase the pressure to shift equilibrium to the side, according to Le Chatelier's principle, but the problem here is that a high-pressure reactor is expensive, so a compromise pressure of 200 atmospheres is used. Now, when we use a lower temperature, then the exothermic side is favored, which means that the forward reaction is favored and more ammonia is produced. However, at a lower temperature, you have a slower reaction as the particles have low kinetic energy. So that's why we use a compromise temperature of 400 to 450 degrees Celsius, and the yield of this process is 10 to 20%. We use a catalyst, iron, in this process, or iron oxide. Catalysts don't have any effect on the position of equilibrium, but they have the rate of reaction increased and the reaction gets over faster. However, please remember that catalysts do not affect the position of equilibrium. Why is Haber process so important? Ammonia is produced industrially, and ammonia is used for fertilizers and explosives, as a cleaning agent, as a solvent, because it can dissolve grease and fats. And industrially, nitric acid is made by catalytic oxidation of ammonia. So this process is very, very important to us. On the other hand, in the contact process, you use sulfur dioxide and oxygen from the air in the ratio 1:1 by molar volume ratio to form sulfur trioxide. Again, you have a temperature of 400 to 450 degrees Celsius if you look at the equation. So you'll understand why we're using that temperature. And we need a compromised temperature, because if it's too low, then the reaction will be very slow. You will learn that in rate or speed of reaction. We have very low pressure over here because the product side has more moles of gas. So we decrease the pressure so that the side with more moles of gas can be favored. And it is important to note that for volume, it is the exact opposite for pressure. So if increasing pressure moves equilibrium to the side with fewer moles of gas, then increasing volume shifts the equilibrium to the side with more moles of gas. Vanadium pentoxide is used as a catalyst to speed up the rate of reaction, but it does not affect the yield or the equilibrium in any case. Sulfur trioxide that is produced can now be used in the manufacture of sulfuric acid, which we require in our industries. Sulfuric acid is used in the manufacture of other acids, fertilizers, and it is used in making detergents, etc. So it has a very wide range of importance. So let's look at how we're going to produce sulfuric acid from the sulfur trioxide we formed using sulfur dioxide and oxygen with vanadium pentoxide as our catalyst and 450 degrees Celsius temperature and 1 to 2 atmospheric pressure. So in the contact tower, the equation that we discussed takes place and sulfur trioxide is formed. Then in the absorption tower, using sulfuric acid, we then produce oleum. Now, if we did not have this step take place, then the sulfur trioxide that is formed, it would have very low concentration. So now when we have oleum, we react oleum with water, and then we have sulfuric acid that is very, very concentrated. If we had not made oleum and we had directly used sulfur trioxide to make sulfuric acid, then as I mentioned, the sulfuric acid formed would be very dilute and of hardly any use. So let's have a look at the contact process in the form of a flow chart. We react sulfur and oxygen in the combustion furnace to form sulfur dioxide. Then we use a catalyst, 450 degrees Celsius temperature and very low pressure to form sulfur trioxide in a contact tower, and then we use concentrated sulfuric acid and sulfur trioxide to form a compound called oleum. Then we mix oleum with water and we get an acid known as sulfuric acid that is very important to us in our industries. So we've covered everything in reversible reactions. Let's have a look at some questions. Chlorine can be manufactured by the following reaction. The enthalpy change is negative, which means that the forward reaction is exothermic. A mixture in dynamic equilibrium is formed. With change to the mixture will increase the amount of chlorine at equilibrium. So we want the equilibrium to shift towards the product side. Adding a catalyst, no, a catalyst does not affect the equilibrium in any case. It just increases the rate of reaction. Adding more HCl. If we increase the concentration of the reactant side, then the equilibrium moves towards the product side and the forward reaction is favored. Let's come back to B again. Then decreasing the pressure. If we decrease the pressure, the side with more moles of gas will be favored. So the left hand side has 5 moles of gas and the right hand side has 4 moles of gas. So the reactant side will be favored. So the backward reaction is favored, and we do not want that as less chlorine will be produced. Then if we increase the temperature, the endothermic side will be favored, which in this case is the backward reaction. So only in B is the forward reaction being favored, is more chlorine being produced, so the answer is B. The reversible reaction below has reached dynamic equilibrium. What does the term dynamic equilibrium mean? The reaction has stopped. No, the reaction still takes place. The rate of the forward reaction is now 0. No, the forward reaction is also taking place. The concentrations are equal. No, they could be different. The rates of the forward and backward reactions are equal. Yes. That's the definition for dynamic equilibrium. The reaction does take place. The rate is not 0, but the rate is equal. In which of these equilibria is the forward reaction favored by an increase in pressure? Increase in pressure moves towards the fewer moles of gas, so we want the forward reaction to be favored. For the forward reaction to be favored, the product side must have the fewer moles of gas. So in A, the reactant side has 2 moles, product side also has 2 moles, no effect of pressure. In B, the product side has more moles, and in C, the reactant side has 3 moles, the product side has 2 moles, so the reactant side has more moles. In D, the product side has more moles, it has 2 moles, and the reactant side has 1 mole, so the answer is C. As the products have fewer moles of gas, so an increase in pressure will favor that side, and so the forward reaction will be favored, and that is what the question is asking us. In the contact process for making sulfuric acid, one step involves the oxidation of sulfur dioxide to sulfur trioxide. The forward reaction is exothermic, so the backward reaction is endothermic, which change would increase the amount of sulfur trioxide produced at equilibrium. Adding a catalyst, no effect. Decreasing the pressure, it should favor the side with more moles of gas, so the reactant side has more moles of gas, so no, the amount of product is not increased, amount of reactant is increased. C, decreasing the temperature. Decreasing the temperature favors the exothermic side, so the forward reaction is favored, which means that more sulfur trioxide is produced, and that is the answer. In such type of questions where it is mentioned specifically that the forward reaction is exothermic, usually the answer has something to do with temperature. We have a very similar question over here. The nitrogen reacts with oxygen at equilibrium, which statement is true. The concentration of nitrogen present will change with time. No. How will it when it is at equilibrium? Then the forward and backward reaction are taking place at the same rate. Yes. The forward reaction releases heat energy. No, because the enthalpy change is positive. D, there are more molecules on the left hand side of the equation than on the right. No. If you calculate the moles, then you see that both sides have equal moles.